And what grade comes just below average?
D.
And just below that?
F.
Just above C?
B.
And above B?
A.
So we looked at this yesterday, right?
Yes.
Okay. And we said that there's a peak in the graph here because that's where the vast majority of those people, of the average people, scored, right?
Yes.
So when we look at data, we try and look at the distribution of data. So we try and see how much variance or variation there is. It gives us an idea of how spread out our data points are. We know that there is a maximum here. The maximum is A. And we know that there's a minimum. The minimum is F. Now the reason Mr. Murphy told you you don't ever want to have your teacher put any of your data on a bell curve, any of your tests on a bell curve, it guarantees the same number of people who get A's and B's get D's and F's. Look at it. It's symmetrical, right? That means the average person in the class would score perfectly average, a 75. And that means 34% of the population would fall between average and that like B range right there. And another 34% of the population would fall right there. It's perfectly symmetrical. How many of you are like, yeah, you can put my stuff on a bell curve so long as I'm the one who falls above the C?
Yeah,
No, that's unfair to my
no,
friends.
I want an A.
Oh, so you recognize it also limits the number of people who get A's, right?
Yeah.
It's a much smaller portion of the population over here who would get A's. Looking at this, we can do this for any data that we collect a large amount of data for. So say if I were to collect ages, we could make a graph for the average age. We could make the graph of the average age of a student at Divine Child High School. So what would our minimum likely be?
13.
And our maximum?
18.
Hopefully 18. We could make a graph for the average age of the people who live in my grandma's old folks home. So what do we think the minimum is in my grandma's old folks home?
65.
It's probably around, yeah, you're probably right around 65 because it's one of those like independent living facilities in one section. And what do we think the high end is at my grandma's old folks home?
100.
112 and a half.
92.
Oh, my grandma just turned 99,
Dad.
so we know for sure that we've got her on there, right?
I'm at 101.
So we can put any data set on a graph like this. We can determine where average is, and then we can see how much of the population falls above and below average. That's what we use a curve like this for. But I pointed out to you guys because scientists use this as a method of data analysis. And we call that being just below and just above. That's one standard deviation above the mean and one standard deviation below. So if you're within one standard deviation of the mean, that means that 68% of the population falls within that window. Now what that window is depends on your data set. So here, the mean is what if it's a C? A flat C, not the honors scale, like traditional scale. Flat C.
What was the question?
What percentage is that? What number is a C? 75. That's average. Perfectly statistically average, 75%. If you are going to fall within one standard deviation of that, you are going to be, I do believe it's 87.5%, so. Within 12.5% above a 75 and 12.5% below a 75. So 68% of the population is going to score in that middle window. Does that make sense? Scientists like to do this with data because it gives us an idea of how variable the variance is. So how variable or the variance. Let's look at ages in this classroom alone. What do you think the average age is in this classroom? 13, 14, what are we looking at?
13.75.
All right, you guys are on average of 13.75 years old.
He's 15.
But who's the youngest person in the room? Do we know?
Probably me.
How old are you?
13
13 even?
and a half. No, more like, and 3/4 more like.
Isn't that exactly what you just told me average was?
Yeah.
So did that make you the youngest in the room?
Wait, when's your birthday? How old are you?
13
When's your birthday?
October.
Yeah, she's Mary's the youngest.
How old are you?
13.
13 even?
No, like
When's your
13
birthday?
and then I turned 14 in November.
Dang it.
Manny Thatcher's younger.
Raise your hand if you're 14. Woo!
Wait, why are we raising our hands?
Stop putting up.
All right.
Come on. Still someone else has it.
I know I'm not a mathematician. But, Ray, keep your hands up. You all just said you are 14.
Why did you guys say 13?
But they're not.
Then why is the average 13.75? Let's just do it.
That's what he said.
I'm never right.
I said 14.
Could you have prefaced your answer with "I'm never right" before I chose you?
No.
Let's make our data more probable.
Alright, it's actually like 14.21782.
That's pretty
3.14.
accurate.
I did it in my head.
Let's say 14 and a half. So 14 and 6 months is the average in this room. If 14 and 6 months is the average in this room, but our youngest is 13, 13 and how many months?
10 months.
13 and 10 months, 10 out of 12 in decimal form.
I don't like this system of you we use like millidays or something.
Millidays. What's a milliday?
Like megadays.
So that means if we're looking at this particular thing, that means the average age in here is 14 and a half years old, but 68% of the students in this room are between 13.75 and 15 and a quarter years old. That's the range. That's what we use standard deviation to tell us. Did I math right?
Oh well.
That would have been an ugly number, right? So, do we get what that tells us when we see the plus or minus behind it? That 68% of the population falls in that range? That's all that means. No?
I don't understand.
Let's see here. Well, for you guys, that's heavy.
Why is it 68%?
Because that's what statisticians have defined as one standard deviation.
Why?
Because it's statistically more than 50% of the population.
Okay, but what's the math behind it?
Let's go with weight then.
Okay.
Say the average weight of individuals in this classroom, now keep in mind I just made up a number. The average weight of individuals in this classroom is 110 pounds. But we fully recognize there are people in this classroom who are under 110 pounds, and we recognize there are people in this classroom who weigh more than 110 pounds. So we found the average. Talking rights have been revoked. So we know that there are people above 110, right, plus, and there are people below 110, minus. It's how many people are close to average that we're looking at. So let's say plus or minus 5 pounds. 68% of you Don't be distracted by the snake. 68% of you fall within the range of 105 pounds to 115 pounds. That's what that plus minus means. That's all it's telling us. It kind of gives us a spread. The larger the number here, the more spread out the data is. The smaller the number, the closer the data is. So we end up with curves with big numbers that look like that, but we end up with a curve like that if we have a really small standard deviation. It's just a measure of variation within a data set. Is variation good or bad in a data set? What do you think?
Bad. Well, depends.
What's it depend on?
Depends on what the data is.
So when would variation be bad in a data set?
Like,
If you're measuring how much of something you should put in something else.
All right, so if you're taking a measurement, you would like precision and accuracy, right? And precision and accuracy means you should probably get the same number over and over again. When does it not really matter?
like, if you keep doing something different, like if your independent variable, say you're doing an experiment and you're changing it, like your how to kill a plant experiment, and you're using different amounts of your herbicide or different kinds, and you get different numbers.
What if I did an experiment and say that experiment involves eating Alestra? What would you expect your results to be, Mary?
For you or for me?
For either of us. So what would we expect to happen if someone ate Alestra? They die. Did that happen in the experiment? Were any deaths reported?
You can't report a death if you're dead.
Another person that took the death.
I'm pretty sure somebody would follow up on that one. Like, you fed my loved one something and they died, I'm fairly certain there'd be a follow-up phone call.
They'd have like stomach problems and stuff.
All right, so we'd expect stomach problems. What if I fed everyone 5 grams of Alestra in this room, and everyone reported 2 stomach problems. Is there a lot of variation in the number of stomach problems reported, or little? Is that good or bad? Okay. So do we only want variation when we manipulate your independent variable? Is that what you're telling me? That's what you said, right? If I was doing my how to kill a plant experiment? Okay. What about ages? Do I care about variation for ages? No. There are some pieces of data where it won't matter, others that it will. There's another piece of data on your Alestra article we haven't looked at yet. You guys skipped it. You read right over it. It's a parenthetical note. Pull that out and see. What, do you think you know what it is? Oh, you need an article. Yeah. Too many parenthetical notes, and it's just so much fancier to say parenthetical note, right? There you go. Do me a favor and find the suspicious thing in the results section. Find the suspicious thing in results. Ready, set, value. And the p-value is simply a scientist's way of looking at data and saying, yes, this is good data, or no, this is bad data. And the way we do it is by performing a mathematical function. So it's essentially an equation. And we subject a data set to an equation, and it results in a p-value. The bigger the p-value, the less likely we are to accept our hypothesis. We're like, no, that the data is not good. It does not fit our hypothesis. I point this out to you because there's something about these p-values you should notice. They are not good. They're pretty big. For scientists, any p-value above that one is too big. You should be like, we don't like this hypothesis. We've got some big p-values here. We have some data here that should be suspicious, including the data that, 31 people couldn't be contacted. So we have to remove them from our data set. This is just a way of saying how good the math is for our data set, whether it's convincing or not. If I told you guys that the data I think works out to, is it 15.7% versus 16.8? Is that the data? 15.8 and 17.6. If I said that 15.8% of the Alestra people reported tummy troubles and 17.6% of the TG people reported tummy troubles, is that data very similar or very different?
Pretty similar.
You're like, those are pretty close numbers. There's not a discernible difference between Alestra and TG chips. Is that how you interpret that data? That's how they're interpreting it with the p-values they've given you. But that's not what the hypothesis was that you gave me, was it? When you told me it was good design or bad design yesterday, how many of you said it was bad experimental design? How many of you said it was good experimental design? Those of you who said there was something rotten in the state of Denmark, my friends, you were correct. There is something smelly about this other than the GI trouble. Come on, it was right there. How could I not take that? So we know that because of the p-values associated with it. And if you read on, you find out that this study was, in fact, funded by the people who make Alestra potato chips.
I told my partner that.
Did you really?
Yeah, I bet they did the Alestra people did this.
The Alestra people did do this. The Alestra people wrote this article. Are you surprised by their results yet? Now you're like, of course they're going to say it's not bad for you. Of course they're going to say the TG chips they cause more tummy troubles because they want you to buy their product. You'll notice it in the very fine print at the very end of the article that that's who paid for it.
It's like those fine print.
Funding for the study was provided by Procter & Gamble.
Oh, but your teacher didn't tell you to read all the way to the end.
Yeah.
Oh. When we have data that we find convincing and compelling in science, and it's repeated data over and over and over and over again, it supports a hypothesis. Does our hypothesis get to grow up? Does it turn into anything else? So a hypothesis that's been supported over and 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 over again grows up and it graduates into what?
Theory.
It's scientific theory. Hey, that was in our read and take notes, right? Do scientific theories change ever?
Yeah.
Yeah.
They can.
Yes, they can. Those of you who said yes, they can, why do you think so? There were a lot of you who said, I'd like to hear all of your answers. We'll start here.
Because people are always trying to disprove it, so someone eventually will.
People are always trying to disprove it. What did we say? Yep. Why do you think, or what happens, or why do theories change?
Because new evidence is found.
New evidence is found? New evidence to the contrary?
Or for both sides.
Okay, so new evidence.
Yeah.
What do you think, Nick? New evidence?
Like, if you do more research, you can provide more backup.
So we always say science is looking for more evidence, and sometimes if the evidence doesn't support the theory, we change the theory. Is it possible?
Yeah.
Oh, I just want to make sure, because sometimes people accuse us of being steadfast in science, and I'd like to make sure that people understand we're very reasonable.
After scientists communicates their results,
Another scientist can absolutely disprove them. Most certainly. I wanted to make sure we knew that.